Hello, good afternoon, good morning. My name is Chiara Benetti, and on behalf of ETA Florence Renewable Energies, technical organizer of IEA Bioenergy webinar series, I welcome you to today's webinar on flexible bioenergy in renewable energy systems. The webinar will be presented by Elina Maki, research scientist, energy production and carriers from the VTT Technical Research Center of Finland, by Tilman Schildhauer, senior scientist, thermochemical processes from the Paul Scherrer Institute in Switzerland, by Daniela Trenn, senior scientist, bioenergy and bioeconomics from the German Biomass Research Center, and it will be moderated by Jaap Kiel, Program Manager, Bio-based Fuels and Chemicals from TNO, the Netherlands. The webinar will be recorded, and the presentations and recording will be made available from tomorrow on IEA Bioenergy website. During the webinar, you will have the possibility to drop questions by using the Q&A tab that you can find at the bottom of your screen. You may use the functionality throughout the webinar, and our speakers will have the possibility to reply to you by simply writing the answer in the Q&A tab or by answering live. Please do not use the chat box for questions, but just the Q&A tab. From my side, that's all. I hope you will enjoy the webinar, and I'll give the floor to Jaap Kiel for the starting of the webinar. Thank you.
Yes, Chiara, thank you very much. Ladies and gentlemen, also on my behalf, welcome to this webinar. Good morning and good evening, good afternoon to every one of you, depending on where you are. It's fine that you would attend in such a large number. And we hope to, in this webinar, to shed some light on flexible bioenergy. I think we've seen during the last years a largely growing share of solar and wind with a steep reduction in generation costs to meet greenhouse gas reduction and renewable energy targets. However, these growing shares of these, let's say, variable renewable energy sources in the energy supply, they bring concerns about guaranteeing an uninterrupted supply of electricity, balancing seasonal imbalances in supply and demand, and providing renewable fuels in all sectors. Bioenergy can play multiple roles and can play an important role to meet those concerns, both during the transition phase, but also in the long term. Flexible bioenergy concepts, they have the potential to provide low carbon dispatchable resources in terms of long-term storage, peak demand and backup, and demand response. However, there is still a lot to learn about flexibility in bioenergy and the possibilities, not only in technical terms, but also in terms of how to create attractive business cases. At IEA Bioenergy Task 44, we focus on that. We aim to create a clearer picture on the role of bioenergy as a flexible resource. And so that not only concerns a better understanding of the technical maturity, the market status, R&D needs of different flexible bioenergy concepts, but it's also important to identify the frame conditions and to see what the situation is in different countries, how they look at the possible role of flexible bioenergy. Well, in this webinar, we want to address basically these two aspects, the technical aspects, as well as, let's say, framework conditions and views in different countries in two presentations. But before doing that, we will have a general overview presentation. In addition to the presentations, we will also have polls to get an impression of your ideas on flexible bioenergy. And let's say as a first poll. Ernesto, could you start that? We would like to get an impression of, well, what sector you represent. So please, if you could fill in this poll, then that gives us an impression of our audience. Ernesto, can you already show some results?
Yes.
Thank you. Well, that's good to see. So clearly most of you represent or are from a research and development background, but it's nice to see that there are also several representatives from industry and policymakers, and also non-governmental organizations. Clearly, I think with all bioenergy aspects, it's important to also to look at the societal impacts, societal consequences. So very good that also representatives from non-governmental organizations are present. So very good. With that, I would like to go to the first presentation that will be given by Elina Maki. She's a research scientist on energy production and carriers at VTT in Finland. And she will give an overview on the role of flexible bioenergy in renewable energy systems. Elina, the floor is yours.
Okay, hi all, and welcome to this webinar also on my behalf. So before we really deep dive in the topic of flexible bioenergy, I want to provide you a little bit background on the topic. So why we are actually looking at flexible bioenergy, and provide you some examples of flexible bioenergy concepts. And I will tell you also how we have in the task 44 defined flexible bioenergy, and also tell you a little bit about task 44 flexible bioenergy and system integration. And I hope that with this background, it's good to deep dive to the technical and market perspectives of flexible bioenergy. So about the background, as we all know, the costs of wind and solar energy has decreased drastically during the past years. Over the past 10 years, the levelized cost of wind power has decreased around 70%, and the corresponding number for solar PV has been as high as around 90%. And the costs of wind and solar are approaching or have even approached in some parts of the world the costs of fossil-based generation. And what happens at the same time is that the potential from renewable energy resources is really massive. This figure shows the offshore wind technical potential from the IEA Offshore Wind Outlook. And what we can see here is that the estimated technical potential in many countries and regions is much higher than the actual electricity demand. So actually two things are happening at the same time. The costs of wind and solar power are decreasing fast, and at the same time, we have a lot of resources available. We have to keep in mind, though, that the output from wind and solar is variable by nature and only partially predictable. And what does this mean for the grid integration? In this figure by IEA, the figure is presenting on the vertical axis the variable renewable energy generation of the total power production in certain countries. And the coloring of the bars is showing the grid integration phase in the same countries. So what we can read from the figure is that in the countries where the share of variable generation is less than 10%, we are in the phases 1 and 2 of grid integration, meaning that that the generation has no relevant impact on system integration, or we can utilize the existing flexibility from the system. But then when we move to higher shares of variable generation to 10 to 20% or even 20 to 40%, we are moving to phases 3 and 4. And this means that we actually need investments in flexibility and also new advanced technologies and approaches to ensure the system reliability. And what's notable is that this figure is from 2017. So many of the countries, for example, in the phase 1 and 2, have already moved to the next phases. So this integration topic is very relevant today. We also have to remember that variability and uncertainty are not new things in the energy system. But all the power systems and energy systems have some inherent level of flexibility that can already balance supply and demand at all times. This is an example figure of demand in an example power system. Then when we move to a system where we have more variable generation, like in this system, we cover 40% of the electricity demand with wind power. The increasing share of variable generation increases the variability in the system. And that in turn creates a greater need for flexibility. This means, for example, steeper ramps, lower outputs, and shorter peaks. And this also raises a question, how can we guarantee an uninterrupted supply of electricity in the system? We actually have already multiple tools for that, or measures. The power system has really many components that can address the flexibility already today, like flexible operation, networks, flexible generation and demand, sector coupling, and energy storage. And here, these are classified according to power sector components, and indicative costs are shown. But those costs are really indicative since they are very dependent on the system and also evolving over time. And there are a lot of opportunities, and likely we will need most of them to integrate increasing amount of variable generation in the system. But in the task 44, we are mainly interested about bioenergy and flexible bioenergy. And we can actually find it in quite many places of this figure. So we have flexible generation. We have also flexible demand concepts, sector coupling, and energy storage, where we have options to provide flexibility with bioenergy. Then if we look in the technical side of flexible bioenergy, there is still a lot of room for development. So regarding biomass boilers, we have listed here 3 different development needs. These include faster cold startup times, increased load change rates, and wider operational range. And this wider operational range mainly means lower minimum loads with proper emission performance and efficiency of the production. And actually, many of these development needs are already addressed by many companies. In addition to technical aspects of flexible bioenergy, we should also think about profitable business models. So in order to provide flexible bioenergy, we have to make the business cases economic. And we think that bioenergy has many unique features that can help in flexible provision with good economics. Bioenergy is, can, for example, co-generate different products with flexible output ratios according to, for example, electricity prices. We can provide different combinations of heat, power, fuels, and other products. In addition, bioenergy is also the only renewable chemical energy source, and it's naturally easily storable both as solid and liquid, and also as gas. So we think that bioenergy has many features that can help to provide flexibility in an economic way. Next, I will show you some flexible bioenergy concepts which we have been considering in task 44. And in these concepts, we have both the base load part, which is marked with blue color, and then we have the flexible part, which is marked with orange. So this is an example of co-production of power, steam, and heat, where combustion represents the baseload production, and then we can produce power and steam with flexible output ratio. And this steam can be used, for example, to industrial drying processes or desalination, and the market conditions define how much we need that. The second concept is liquid fuels from peaker plants. And the idea here is that we have biomass feedstock, which like wood chips, which is already a renewable chemical energy storage. But if we convert that into liquid form, for example, through pyrolysis, we can make it even more easily storable. And with this storage, we can decouple the conversion process and the end-use application of the bio-oil. So we can produce flexibly electricity on demand. The next concept is about co-production of fuels, power, and heat through gasification. And here we can produce power and fuels according to, for example, electricity price. And the last concept is about demand-side flexibility from bioenergy. So here we are producing methane through anaerobic digestion, but actually we can also produce hydrogen from surplus electricity and use that hydrogen to boost the methane production. And that way, the methane is actually working as a chemical energy storage for the surplus electricity, for example, from wind and solar. And as you can see from these different concepts, we have really different options to provide flexibility from bioenergy. And here you can see a qualitative representation of different options. So we can produce flexibly peak power from biomass through co-production plants or in backup plants. We can have flexible boilers, and we can produce hydrogen-enhanced biofuels. And then furthermore, we can utilize the storability of biomass and then use these produced fuels during the times when we most need energy. And well, as you can see, there are a lot of different bioenergy concepts, and also they include very different dimensions of flexibility, like feedstock flexibility, operational flexibility, end product flexibility, and flexibility at different time scales. So what we found out is that it's really challenging to capture all these dimensions into one definition for flexible bioenergy. But we did our best, and where we ended up is a definition like this. So we have defined flexible bioenergy as bioenergy system that can provide multiple services and benefits to the energy system under varying operating conditions and or loads. And this includes different examples. For example, technologies that can provide grid stability for a power system with large amounts of variable wind and solar energy. It includes dispatchable production of energy and other products according to market demand. Poly generation systems combining the production of heat, power, fuels, and chemicals. It also includes long-term storage options, for example, in the form of biofuels and biochemicals, and ancillary services to support system reliability. And this is now the definition for flexible bioenergy, which we are using in task 44 to support our work there. Then to the end, some words about our task 44, flexible bioenergy and system integration. So we are covering there flexible bioenergy from different perspectives. The first one is the technical perspective, where we study flexible bioenergy concepts for supporting low carbon energy system. And the next presentation will be actually about this. And we will soon launch a report on technical options to provide flexible bioenergy. And there we will present, for example, different categories to provide flexibility. The second topic is about acceleration of implementation. And we launched actually today a report on that. So expectation and implementation of flexible bioenergy in different countries. And you will also hear about the key findings of this report in this webinar. And as the last point, we are addressing system requirements for bioenergy concepts. At the moment, we have 9 member states, which are Australia, Austria, Finland, Germany, Ireland, the Netherlands, Sweden, Switzerland, and US. And in the end, I would like to invite you all to join our flexible bioenergy community. So we have a LinkedIn group called Flexible Bioenergy, where you can ask questions about flexible bioenergy and share news and see the news we are sharing about flexible bioenergy. And then we also have Task 44 website, where we share, for example, reports and publications from our task. You can also find the recent report launched today from there. So thank you for interest. And I also want to take the opportunity to tell you about another webinar on flexible bioenergy, which will take in April. So you are very welcome to join that as well. It's from the project called Vabisus. Thank you.
Thank you very much, Elina. And I must say, when I introduced you, I forgot to say that you are actually leading the IEA Bioenergy Task 44. And we experienced, well, since a few months, and we are very happy with that. And so to the audience, if you have further questions, also please, also after this webinar, please contact Elina. In the presentation, you will see her email address, so she will be open to all your questions. Also now there is a question, Elina, that is on your statement that bioenergy or biomass is the only chemical energy source which is non-fossil. So the question is, what about power to X? So options, let's say, with based on CO2 and hydrogen.
Yes, there are definitely different options where bioenergy is related. And actually what we are doing increasingly is to cover also those options in our work.
Okay, thank you. Would you also like to reflect on the poll results?
Actually, I don't see them at the moment.
Okay.
Click on polls.
Jaap, if you found them, could you please, because I'm not able to find them at the moment.
Yeah, I can mention them. I don't know. I think then you have some time to look them up. So the question was, and to the audience, well, you saw this poll just popping up. That will happen several times more during this webinar. So don't be surprised, let's say. And it's good that you reacted on it. Here the question was, where do we most need flexible bioenergy in the near future? For long-term storage as a chemical energy carrier, 44%, and for backup source and peak generation, 46%, and to a less extent for negative ancillary services. Well, I think in the presentation of Elina, you already saw several options being highlighted, and that is largely in line with the outcome, or let's say with your impressions. In the next presentation, we will dive into this in more detail, and that will be done by Tilman Schildhauer. He's from the Paul Scherrer Institute in Switzerland, and there he is a senior scientist in thermal processes. And in addition, in the IEA Task 44, he is the national team lead for Switzerland. Tilman, I think the floor is yours. And perhaps you can also take this poll outcome into account in your presentation.
So, yes, I will do. Thank you very much, Jaap, for this very kind introduction. And also welcome to everybody from my side. I'm quite happy to walk you a little bit through these technologies which we have here. And I was actually quite struck by the outcome of that poll, so that most of you don't think that negative surfaces are so important in the near future. But for the long-term storage and for the peak generation, this is about half-half. And actually, we will see that it's somehow also reflected in the technology development, which I'm presenting now. So I would like to take the next 10-15 minutes to walk you through this energy landscape. And maybe put this in a laser pointer here. Okay, so this is where we find the biomass. So we have, that's one of the specialities of biomass, that we have different sources, different types of biomass. So we have dry biomass, which can be stored. That is mainly something like wood or wood residues. That could be straw, things like that. And we have wet biomass, which is often enough not storable or is decaying relatively fast. And we also have renewable electricity, which we know can be very variable. On the other side, there's the applications which we have. So we want to have heat, we want to have electricity, maybe produced together with this heat. We want to have transport, we need feedstock for chemical industry. We might also in future need CO2 from biomass for negative emissions, so for bioenergy, carbon capture and sequestration. And now we have to come somehow from this side to this side. And there's two steps in between. We have something like intermediates. So these are gases or liquids, or maybe solids, which cannot be so easily transported and stored, which maybe still undergo further chemical reactions. And we have energy carriers. So these are more or less things which we know, where we have infrastructure which can be stored, where we have also a very good distribution infrastructure, so we can actually use it at a different time and also a different place than its production. Okay, and this gives you a little bit of example. So intermediates which cannot so easily be stored is clearly biogas. Producer gas from gasification is usually something which is not stored pyrolysis oil is storable, but might undergo some chemical reactions if we wait too long. And at the moment that we don't have a hydrogen infrastructure, then usually hydrogen can be stored maybe for a couple of days or very few weeks, but not longer. And the energy carriers, then we see things which we know quite well: wood pellets, wood chips, which are transported all over the world. We have methane or liquefied natural gas, maybe some mixtures of methane and CO2. There's the stabilized pyrolysis oil, and then all kinds of the non-liquid fuels like methanol, Fischer-Tropsch diesel, and things like that. As Elina already showed, we have these different dimensions of flexibility. So we have this long-term flexibility where we want to convert bioenergy into something which can be stored and into an energy carrier. But we also have these two dimensions, the positive and negative, on the electricity system, where we either want to supply electricity when the system is short of electricity, or if there's too much, then we might want to take electricity up and actually maybe convert it to something which can be stored to then later use it over here. So these are the three dimensions, but actually we also have different levels. We have technologies which already exist, and that means they work technically, but there's also an economic business case, so they are applied to a large extent. We have emerging technologies. These are usually demonstrated technically, so we know that they work technically, but they're not applied so much because there is no business case yet, or it still has to be organized, and they are the ones which are still under development. And I want to give you walk a little bit through what is already there, what could be realized in relative short time if we give the right financial incentives, and the things which really need some time more on the technical development. Okay, let's start with biogas. So we start down here with the wet biomass. So that could be sewage sludge or manure or some leftovers from the food industry. And the first thing what we do is we create biogas. And this is actually something which anyway would happen naturally. So if you just dump it somewhere, that it might produce methane anyway. But we now do it in a kind of a controlled environment, so that it would be more an agricultural one. And this is how it usually looks like close to a wastewater treatment plant. So we have this anaerobic digestion, and we produce actually a mixture of methane and CO2. And this is done all over the world. So we have way more than 10,000 plants. And some of these actually have a storage capacity for the raw biogas of several hours or maybe half a day or so. And this capacity storage is important later to give us some flexibility. Now, once we have the biogas, we can do different things. This is shown here. There's actually two things which are competing with each other. One is I take the raw biogas just as it is. I do a little bit of a gas cleaning, and then I go into an combined heat and power plant. So usually something like an internal combustion engine, like this one, where we produce electricity and heat. And these things are really widespread. So we have many of these, several thousand. They can ramp down relatively fast within minutes, and they're very flexible. So you can go from 0 to 100% load. So that happens at many places. Still, we have to say that most of them are not operated as flexible as they could be technically, because for the financial reason or economic reason, it's more attractive at the moment to run them more or less base load, 100% all time. But together with this possibility of biogas plant to keep the gas for some hours, that actually could become a very fast implementable solution for peak or backup generation of electricity. The other thing which is done also at many places is biogas upgrading. So we take the biogas, we want to inject methane into the grid because the grid contains mainly methane. So there's some injection specifications which we have to fulfill. And the most important one is that we have to decrease the amount of the CO2 a lot from the biogas to produce biomethane. And there's different technologies to do that. So there's scrubbers based on pressurized water or amines. There's pressure swing absorption. Meanwhile, there's a lot of these membrane units like shown on this photographs. And most of them have very fast ramp up and ramp down. And in principle, you could even switch between these two. Usually it's not done for economic reasons. once you have the gas in the grid, the methane, you could liquefy it or use it right away, and then you could use it, for example, also for heating, or you use it in combining the power plants at a later moment, so not directly, but after transport in the grid to another place, maybe also some storage to a later point in time. Or you could use it for transport, either as compressed natural gas, like in this passenger car over here, or what is coming up now is that we liquefy the biomethane, so we have liquefied methane or biogas, which could be used for trucks, which would like to operate on renewable energy, but have a very heavy duty or very long distance to ride, so that it cannot be covered by either electricity or hydrogen. Okay, now if we have some of this additional electricity, which we at this place where it's produced, we cannot use it, and we can also not transport it away because maybe of some limitations in the electricity grid, then we might want to produce hydrogen from it by electrolysis and add it to the raw biogas, because that would allow us actually, instead of separating the CO2, we could actually convert the CO2 into additional methane. So from the same amount of biomass feedstock, we can produce 65% more methane. So this is quite attractive from that point of view. But you need that hydrogen. So technically it's possible. So we have several plants in TL8. So this is a 3 megawatt plant in Germany. There was a close to 1 megawatt plant in Switzerland, and there's a similar one in Denmark. So there is several plants, but not more than 20. Many of them even smaller than technical rating level 7 to 8, both on either biological or catalytic methanation. When they are warm, they can start up within 20 minutes, and they have also some load flexibility, especially the biologic one can actually ramp from 0 to 100 principle. What you see, it's yellow, so it means that actually then corresponds to the small number. It means technically it's more or less possible, but at the moment are very few places only where you can run it under commercial operation. And there's actually a kind of an addition to, if you take up hydrogen, so that would be the negative service to the electricity grid. But at the moment when you don't do that, so you don't have the additional hydrogen, and you would want to have to feed methane into the grid, so you have to separate the CO2, then in principle it would be available for sequestration. So that would be actually a source where you can capture the CO2 and bring it to sequestration place, and by this have a real negative emission. And from that you can already see biogas plant actually could in winter, when there's not enough electricity and we don't have hydrogen, then you could use it for negative emissions. But maybe in summer, or when it's a very windy time, and you produce way more electricity than you need, you produce hydrogen, and then you would, instead of giving the CO2 to sequestration, you would use it to produce additional methane. So that gives quite some flexibility on one biogas plant. Okay, that was the biogas part. Now I would like a little bit to look at what can we do with wood, mainly, so dry biomass. And there again, I mean, most of the wood which is used today is immediately used for heating. So that is actually the very first use of that, and that has some flexibility in itself, because you actually can stop it or start it again. And also there are some systems for ramping it up and down, the heating, if you need it. But if you look more into the overall energy system, then what comes into the picture is actually combined heat and power plants based on wood. Most of them are based on combustion of wood, and then you operate a steam turbine or an organic Rankine cycle. There are few first plants, usually relatively small, which run on pellets, where we have a gasification and then a gas engine afterwards. So that actually is a combustion with the steam cycle, and this is a pellet-based gasification, CHV, both in Switzerland. What you can see if you have a combustion part or a gasification part, so they are not flexible, so you cannot actually completely stop their operation so easily, but at least you can go to some part load. While once you have the gas, you could either burn it or produce electricity in the engine. And if you have a steam cycle, then you're actually always able to bypass the turbine, which makes actually that you can be very flexible with the turbine to produce relatively fast your electricity. Another option, what you can do with biomass, with dry biomass is undergo pyrolysis. And pyrolysis, you see here, this is a photograph from the Netherlands. This now has more or less reached commercial status. This is why I made this as a yellowish and green arrow, because some of them are more or less commercial, others are still demonstrated but not commercially applied. As I mentioned before, that is not necessarily too long storable. So the next step clearly would be that you do a kind of a stabilization with hydrogen. So that's actually mainly to saturate some double bonds and maybe remove some of the oxygen from the oil, which actually also improves the quality quite a bit. And this way, then you get something which is very, very stable and very nicely transportable and storable, and then could be used clearly later for pickup generation or so. In principle, we could also go from the pyrolysis oil also to transport fuels or even to produce some intermediates for the chemical industry. Another thing what we can do with wood, so wood is in that respect very versatile. We can actually have it undergo gasification. So I have here a photograph of the gasifier in Austria. Actually, they are not, once it's gasified, then you can actually operate a large gas engine. There are some of these around, some of them really in large scale, so several megawatts. And technically they work quite nice. The ramp up and down of the gasification again takes a day or so, but the gas engine itself again is very, very flexible. And most of them operate under commercial situation, but situation became more difficult in the last years because the wood price is going up and the electricity prices in average are a little bit going down to some at certain times. But you can do more with producer gas. Actually, you can produce either methane or liquid fuels. So for the methanation, I show here two pictures. This is the Gobbi gas plant. Unfortunately, the lower part is cut away, but it's the Gobbi gas plant, which is a very large one, 32 megawatt thermal input. And this is a demo plant, which was in Austria, around 1 megawatt input. Again, the gasification part can ramp up and down within a day or so. Such a methanation plant, if it is warm, you can actually start the methanation within 30 minutes and produce methane, which more or less fulfills the injection specification. Another very nice picture, which I wanted to show over here, is actually this beautiful plant where we have actually torrefaction step in between. We have a trained flow gasifier, very large scale, produces syngas, which then is actually converted to liquid fuels in this plant in the northern part of France. And again, from both processes, there's always, because biomass contains oxygen and these fuels don't contain oxygen, there's always some CO2, which in principle could be used for negative emissions. Again, technically it's possible, but it's not yet done. Also, all the other processes clearly are all in demonstration phase. And also here, in principle, it would be possible to enhance the biofuel production, both for the methane or the Fischer-Tropsch or the methanol with hydrogen. It's fully obvious that it works technically, but it has not yet been tested in large scale or demo scale so far. So there's some research needed still. Okay, as you see, flexibility is a complete network, so you can more or less have all kind of flexibility from all kind of resources, so that is quite nice. But you can also see it's quite diverse from the degree of implementation, and that is a little bit again 50-50 reflected over here. So now I took the table from the beginning where we have here the dimensions of the flexibility, and here's the different levels, how far we are. And then we see the ones which are economically and technically feasible is the biogas upgrading over here, and it's biogas CHPs and the wood combustion with steam turbines. This is mainly that what is happening here. Already the wood gasification with an engine after that now is a little bit becoming under trouble. So we have many technologies which work, but are not yet feasible, and still a lot of things in the pipeline. And what strikes me so much is when you said we need it for long term, that is what we see here, and the other half said we need it for peak generation. This is what we see here, and only 10% of you had the feeling we need it for negative services, and this is what we can see here. At the moment, there is no commercial application of that. There's no incentive to operate one of these plants so far, based on to have a negative ancillary service for the energy system. That actually brings me a little bit to my summary. So we have many well-developed technologies, and most of them have been demonstrated. Besides combustion of woods, there are only a few business cases which really work, and this is starting with a waste stream. So if biogas is produced from waste streams, which you anyway would have to take care of, now you produce something useful from it, because you cannot just burn it. And producing electricity works at many places. We have, however, to keep in mind that in most countries which applies that there is some support scheme in place to have electricity from biomass. So it's supported financially, and if you want to use it in a flexible way, how we will need it in future, it means you need an additional support. You need special incentives to really operate them in a flexible way. At the moment, most of them have the tendency to operate in baseload because it's more attractive from economic point of view. Yeah, so with wood, it's especially a problem because you have combustion as an alternative, and there's many fossils which actually can be used as alternative feedstock. So the business cases are not that easy. We think flexible hydrogen addition to fuel synthesis can make a lot of sense, but it's under development. And to sum all that up, and this is more or less my key message, are the lower 2 points. So we can do flexible peak electricity, we can do CO2 mitigation, and actually even negative emissions. We can do negative balancing power. All that we will need in the future energy system, and bioenergy can be part of that. However, at the moment, these features are not as high valued or esteemed as you would appreciate it if you would like. So there's too few incentives at the moment to really make that happen in reality. And with that, I'm at my advertising point. Also, there will be a report on all these technologies where you can look up all the details on the different technologies. Our goal is to deliver that somewhere during spring. And here I have to thank all my colleagues in our own task, but actually also from the technical task on combustion, gasification, biogas, and biofuels, which actually were so kind to do some proofreading and give us advice there. And I would like to thank you for your attention.
Tillman, thank you very much for your presentation. I think that has raised several questions, so maybe good to go into them. The first refers to, let's say, the development status of different technologies. And a specific question is when to expect gasification with capacity of 100 megawatt plus. So biomass gasification. You have an idea on that?
Oh, yeah. So the first thing about biomass gasification large scale, I mean, there's always a logistic problem, right? Or a challenge, let's say like that. So if you see this plant of this size, there will be somewhere in Scandinavia or somewhere we have a big harbor around, so that you can transport all that wood to these places. So Scandinavia has this vast experience in paper mills in very large scale. So I think this is the place that we will see it first. Actually on the continent, so in the middle of the continent, it's very difficult from the logistic point of view to have plants of more than several 10 megawatts. I guess this is the first starting point. Yeah, and then clearly, I think it will first happen in the Scandinavian countries. The time, so it depends on the incentives. I mean, there's been several projects like the Gobi gas plant. Actually, it has 32 megawatt thermal input, and that one was the idea was that this one is a TL8 plant to be a model for something which should be built even larger. It was idea was to have 100 or actually expanded to 100 megawatt, and at the end with the price differences, actually the price difference between the wood cost and the biomethane costs became too small, and then it was decided to actually postpone this plans until a point where the incentive is high enough to really do it.
Maybe good to add that I would say the gasification technology itself is available at large scale. So these installations can be built and also have been built when it comes to heat generation. And there are no clear technical obstacles, I would say, to also apply them for other applications. And then it's indeed a matter of logistics and of course also of economic conditions, whether that happens or not. Another question is on the examples you gave on biogas. There is a question, well, what about the digestate? Shouldn't we use that as well for energy production or as a fertilizer?
I have here the tendency to rather use it as a fertilizer, because actually the digestate contains a lot of nutrients. So then, or if you want to use it for an energetic point of view, we have to make, there are two things. First is that all the nutrients are becoming ash in many energy conversion steps. So then we have to handle the ash, which sometimes can be very nasty because it could melt or so. And we have to make sure that the nutrients can go back to the nature. So if you solve these two problems, then there is nothing to say against it. There are also these hydrothermal processes which actually do the separation of the nutrients in the step before the conversion, and then all the nutrients are going back. So that is not an easy feedstock, let's say, for energy conversion, and we have to solve the nutrients topic, especially. I mean, if you start with also phosphorus, we should really have a good eye on.
In terms of not an easy feedstock, there is also a question on lignin. What about lignin gasification?
Yeah, I'm not so much a specialist. Actually, most of you know that better than me. Yeah, I know there has been this Chemrec process in Sweden, which worked quite well. I am not really sure about the status there, so I would have to look that up. But in principle, it's possible. It has been demonstrated.
Yeah, well, in general, of course, when looking at biorefinery concepts, you have to go for a complete valorization of the biomass, so of all the fractions. So if you convert to sugars and lignin, then it's important not only to focus on the sugars, but also have a good application of the lignin. And well, depending on the quality of your lignin, I would say gasification can be an option, indeed. Then there are some questions concerning the options with hydrogen. First of all, of course, what is important there is the carbon-hydrogen ratio. And let's say the mismatch between the ratio in biomass and into the products. If you look at it that from that perspective, what would be the best products or the best conversion technologies to go for? Do you have an idea of that?
I mean, that's the point. I mean, most of the energy carriers which we use today, or which you aim at, don't contain any oxygen. So that would be true for diesel or for methane. Methanol contains a little bit oxygen, but not as much as is in biomass. So we always have to get somehow the oxygen out of the system. So that means if we don't add hydrogen, then this oxygen leaves the system as a CO2, which then, because it's biogenic, CO2 would be available for sequestration. And if we have hydrogen, then we actually can use the hydrogen to leave the system as water, right? And that allows us usually, because then we have more carbon for our fuel synthesis. So the addition of the hydrogen allows us always to produce more of the fuel or the feedstock or energy carrier which we want to have, and it solves the problem to remove the oxygen from the system. And having said that, then it's somehow clear that systems which use hydrogen to produce more fuel, they should become more flexible, because what you should avoid is that you run a process which needs renewable hydrogen all year, because that might be a problem, at least in some regions on the planet, in times when there's not enough electricity available. So especially in winter times, when there's no PV production and maybe there's 2 weeks of no wind, then we can run a problem with hydrogen. So it would be always good if you have a hydrogen addition to a biofuel synthesis to make it in a way flexible, so that you can avoid that you have to use hydrogen in the wrong moment.
Okay, I think we can take one. Well, indeed, let's first have a look at. Well, let's do that later. Perhaps there is one or more or two questions. There are many questions, so I think we will also see whether there is some time in the end to address those. I think we have to slowly move on to the next presentation now. So let's keep them in the Q&A and see whether we can address the remaining questions after the last presentation.
Okay.
Well, Tilman, thank you very much for your presentation. And in terms of presentations, it may be good to mention that the presentations will be made available on the IEA website tomorrow. And we will put the link for those presentations in the Q&A. So then you will be able to let's say download it there and have that link and see tomorrow and be able to access the presentations on that via that link. Well, now let's go to the third presentation, and actually the poll results shown now are, I would say, a perfect introduction to that presentation. This presentation will be given by Professor Daniela Train. She's heading the Bioenergy Systems Department at DBFZ in Leipzig, Germany, and also there has assignments at the university and at the Helmholtz Institute. And in addition, in IEA Task 44, she is co-lead of that task and national team leader for Germany. Daniela, perhaps I may, well, now the poll is already gone, I see. And still, could you still again show the poll? Because perhaps, Daniela, that might be a nice introduction to your presentation.
Can you hear me now?
Yes.
Okay, I had problems to unmute me, but however, thank you very much. Yeah, for your introduction. Yes, there are some hurdles on the way to flexible biofuels, and this was also a question we asked the experts from 11 countries in our activity, expectation and implementation of bioenergy in different countries. And what I will present in the next 10 minutes is an overview of the report, which has been launched today in the morning. You find them on our website, and I it includes the work of more than 20 experts from 11 countries. Our leading question was, what is the state of the art of flexible bioenergy in the member states? And we did not only go for the IEA member states, but also beyond. I will show you soon. What are the bottlenecks, technically, economic, and systemic, that hinder the implementation of flexible bioenergy? And what kind of market and policy measures are needed to overcome the hurdles and to succeed in the introduction for flexible bioenergy in the energy system? Survey is based on information given between end of 2019 and beginning of 2020, and then have been reviewed over 2020. And the report is available on our publication site. So who did contribute? We had countries from all over the world, or all the OECD countries: Austria, Australia, Denmark, Finland, Germany, Ireland, Italy, the Netherlands, Sweden, Switzerland, and United States. And the share of bioenergy use in those countries is it's mainly modern biomass, and it's between 3 and 35% of the overall final energy supply. So wide range. What you find in the report is, for each of the country, a dedicated fact sheet about the status quo, about flexible energy capacities as far as they are not known, about the legal framework, including policy instruments, but also opportunities, barriers, and I will show you this phase-out strategies. Then the key sectors and key actors in which flexible bioenergy should contribute, goals and expectation, and then also what is ongoing research, development, innovation, what do we expect in scenario and forecast, and what about best practices. So I warmly invite you to have a deeper look in the report, and what I will show you now in the remaining time here is only really a summary if you put all these 11 countries together. First thing, what is not very surprising is, yes, we have bioenergy applied in all sectors, heat, power, and transport today. As I said already, we have big differences in the contribution between the sectors and the countries, 3 and 35% in overall contribution, but also between the countries. And there's also a big difference in the energy background of the countries. So for example, here you see just the power supply in the different countries, what kind of energy carriers are providing power today. And here you see already you have some countries with high shares of, for example, water, hydro energy, which is an alternative renewable flexible energy. We also have seen that most of the countries have coal exit strategies, some already till 2025. So there's an overall expectation that the relevance of flexible energy provision and also flexible bioenergy will increase during the next decade. The most ambitious coal exit strategies are already to be realized during the next 10 years. So what can we see with regard to the integration of variable energy sources and in the different countries? What we tried here is to show you which level of integration the different countries have. This is a level 1, 2, 3, 4, and 5. And just to remind you, level 1 of this IEA classification means no relevant impact of system integration. Level 2 means drawing on existing system flexibility. Then we have the level 3, investing in flexibility. Level 4, advanced technology to ensure reliable reliability is necessary, and 5% we have a fluctuating or variable renewable energy surplus for days and weeks, or then maybe in the longer term even seasonal. So what you see is that the countries we have investigated, most of them are already in the phase that they are discussing about investing in flexibility in general, not only bioenergy flexibility. And we also have given here the share of biomass and biomass CHP in the power, or the provision of biomass in the power sector. And you see we have not a very clear picture here. Some countries have a high share of the power sector, but not such a high demand for flexibility. Finland, Sweden, Austria, we might discuss about hydro here. And on the other hand, Denmark is a kind of a forerunner with regard to their flexibility and also their biomass in the energy sector. However, most of the countries have a reasonable share in the energy sector of bioenergy between 3 and 8%, and are in this starting investigation phase. What we also see here is how well are countries informed about flexible bioenergy capacities. And the green countries are the ones who have information available. The blue ones say, oh, sorry, we do not have information available. And from the black countries, we didn't get any feedback. So what you see is still at least half of the countries are not even aware how much flexible bioenergy is provided in the energy system. So we see the countries are in the different stages of integration of variable renewables. We do not see a strong relation to the power provision system transformation. And what I will show you in the next slide is, of course, countries do not only expect flexible power, but also other systems. We asked the countries, okay, what is your expectation or reason to support flexible bioenergy? And you see here, and this is very much in line with your expectations at the beginning, it is about substituting fossil fuels, so this means acceleration of the energy transition, but then also more offering flexibility for the energy system in general, support biofuels, support CCS, heat use, reducing energy costs, or supporting the system transformation. And this is, of course, not so surprising, because I mean, we said that our definition is that flexible energy can provide multiple services and benefits to the energy system under varying operation and varying loads. And we also have seen that this expectation of these additional benefits from flexible energy also go beyond the energy system. So, for example, it was also mentioned to, for example, have a prolongation of the value chain in the agricultural sector or in the industry sector. So what about the hurdles? And here I come back to your last poll. And again, you are very much in line with the feedback from the country experts. What is seen in most of the countries as a big hurdle is the lack of regulation and policy. It is followed by, in some countries, we see competition with other flexibility options. But also economics reason and market mechanism are very important points. So regulations and policy condition, we have also asked what kind of regulations are in place, and we so far have only 2 countries which have dedicated support for flexible bioenergy provision in case. So far, this is Germany and Italy, and it's mainly to, let's say, support a flexible power provision from biogas. There are also some stipulation mechanism for biomethane, supporting biomethane, for example, in Austria. So we see what is in place so far is mainly related to the biogas sector. Additionally, most of the country mentioned some indirect effects, for example, from the low carbon fuel standard in the United States or from the RED II renewable fuel quotas on European level. Those, so there is, and many countries also mentioned that there is seen this need for additional regulation and support. And from my expectation or my conclusion is so that we can expect additional initiatives here, at least if we really want to fulfill the energy transformation and exit, coal exit goals. Okay, so in the end, then we saw, okay, there are really many different approaches and ideas how and where to use flexible bioenergy. So to get a good idea what is really possible, we also have a chapter on best practices. We collected more than 30 best practices from many countries. I just give you a selection here. The examples cover temporal flexibility, to ramp up and down, and also product flexibility to change, let's say, shares of products and also switch between products, as we have heard already from the previous speakers. As what is a conclusion of our exercise is that the best practice is very strong embedded in regional circumstances like regional policies, resource availability, but also it is a central question about energy infrastructure. And this does not only mean grid and power infrastructure, but also, for example, district heating systems, gas grids, and natural gas grids, etc. So this leads me to the conclusion. When we did the whole exercise, one conclusion was that terminology and definition is still not very established. So what is the whole picture of flexibility caused a lot of questions, and we hope we can improve this situation with our IEA Task 44 work. We have seen that chances and barriers for integration variable renewables are seen as the main chance, or this interplay with solar and wind, but it also goes beyond this field. The biggest lack is a regulatory policy framework and adjusted financial regulation. But we have also seen, I didn't go into this field, and this is very much linked to my first point, many, let's say, stakeholders need better information, for example, politicians, but also energy sector related stakeholders to really understand the chances for flexible bioenergy. We see best practice examples as a very promising starting point for acceleration of implementation. And last but not least, of course, there's also more research necessary for system integration, sector coupling, and also these economic aspects. And this goes directly in the direction we heard already, the question from the auditor. Thank you very much.
Thank you, Daniela. There are several remaining questions. I think first some questions to you. It appears first that there is some confusion about, let's say, biorefineries versus bioenergy, or let's say how narrow we see the definition of bioenergy. And well, I would say basically we don't see it narrow. So this certainly also includes biorefinery concepts, especially those where we look at biofuels, but also in a broader sense. I think you've seen that in also in the presentation of Thielman. But of course, this is IEA bioenergy, just so that might lead to some confusion. But be assured, I would say to the entire audience, that we when talking about flexible bioenergy, we look at it really in the broad sense of using biomass for various purposes, including biorefinery concepts. That's true, Daniela?
Yes, I fully agree. Thank you for this clarification. And maybe, yeah, we can give also the hint that we just had last November a workshop with people from biorefineries to discuss exactly this. How can flexibility in biorefinery improve their business concept?
Very good. Then there is a question on support schemes. What would be a good support scheme for flexible bioenergy?
Yes, the existing support schemes from Italy and Germany, which mainly focus on providing flexibility in the power sector, they support plant operators to build additional capacities for their power provision from biogas. For example, in Germany, if you build a new biogas plant, you have to build about double capacity in CHP units compared to the capacity of the biogas plant. So this is the expectation that you then go into, let's say, high price phases, which means support the electricity system. In Italy, there's also a system where you get additional support for providing certain capacities. And I think it is, if you look on a broader spectrum, it is really the first question for support schemes should always be: is it for the power sector or is it more for a broader sector? You've seen the demand for really providing these additional flexibility in different energy systems is different. And what I think could really help as a first or as an additional support scheme we often forget about is the reasonable CO2 price. Yeah, because I mean, then you really get in a better competition between renewables for providing low carbon power, and this could be, from my point of view, an additional important support scheme.
So, but in general, I think also in the poll, the economics were seen as the main hurdle. Would you agree that although there are some examples of support schemes or support mechanisms, that this really is something that has to be developed further, and that we have to dive into how to create, let's say, good economic conditions for application of flexible bioenergy?
Yeah, I fully agree. And maybe just to add on this, on one hand side, we have this pure market related aspect for the available technologies. I gave the examples here, but of course it also means to support the market introduction of these more still under development technologies. Yeah, we heard a lot of them from Tillmann, and there you need other mechanism. I think, such, for example, more demonstration and good practices, etc.
There's also concerning the let me see the question. The negative services. So for maintaining the grid quality, is it also so that that has not been really picked up because the shares of wind and solar are still, let's say, not that high that is absolutely necessary?
Yeah. So for the time being, it is still a competition for providing this. For example, if you look, or you have two ways to support this grid stability. One is to provide system energy, and this means that you curtail your plant for certain times where there's an over supply with electricity, and I think those mechanisms are here in some countries already established, but this is only about this is only a small market, and typically you cannot build a business case on this element only. And if we expect longer phases for negative services, then we are still at the beginning, as already Tilman said.
Okay, then well, you showed a nice overview of the situation in different countries. There is a question whether in certain countries with a lot of hydropower, that isn't it logic that there is lower interest in flexible bioenergy, because hydropower basically can offer a lot of services to balance the grid and to meet the variations in solar and wind.
Yes, this is what I try to say. It is logic, and in those countries we have higher interest in other kinds of flexibility. For example, combining BTL production with, just giving you one example, with heat provision in wintertime, yeah, or so things. So it is not that there's no interest in flexibility, it is more about, let's say, other kinds of these bundle of options are more interesting.
Okay, well then there are some questions on pyrolysis oil. I would say that those are probably too detailed to discuss here. I would like to refer people, when it comes to these detailed questions, to the tasks specializing on those technical topics. But what we still have left is the last poll, which is on, well, what is the role of flexible bioenergy beyond 2030? And well, you see the results here. Do you see them as well, Daniela?
Yeah.
Yeah. So yeah. It is a mixed picture.
Yeah, I think we really see that we still have very different expectations for the long term. And from my point of view, we have one reason is that even if you go for this longer term energy system analysis, you typically have often a precondition where bioenergy is used, and you so far do not elaborate the options of flexibility very well. And this means, from my point of view, also, let's say, something we in our task want to better understand exactly the question, what is the long-term role of flexibility? It depends on the overall demands of the long-term expected energy systems, and also a better understanding of this value of flexibility. We have also heard about this from the discussions, and we see this as a really open question we will work on during the next years.
Yeah, I fully agree. I think it's clear that when it comes to assessing the possibilities of flexible energy, that we're still at the beginning. Of course, we are this situation that solar and wind shares in the energy supply are increasing is relatively new. And up to now, actually, when it comes to bioenergy, we have not really looked at it in many cases as a flexibility option. It is clear for when you look at the possibilities that the possibilities are large, but of course we need to develop a further thinking on, well, what are the preferential possibilities, and that certainly will also be country specific. So further thinking and also further development of both on the technical side, but also very much on the economic and regulatory side is needed. And I think that's the core task, or at least IEA Task 44 tries to make a major contribution to that by bringing together the thinking in different countries in this platform. I think with that we slowly come to a conclusion of this webinar. We still have questions coming in, but I think we unless well, I could ask the panelists whether they saw questions on which they would like to react particularly. We have some minutes to do that. Tilman or Elina, or Tilman, would you please go ahead?
Yeah, there's a big choice. So many thanks to the audience for asking so many interesting questions. Actually, more questions than we can answer, and sometimes, at least, I'm not competent to answer them. There are actually two which I wanted to pick. One was a question: what to do with cow dung, and then clearly manure, things like that. You would always be able to do digestion. That is an easy one, which is actually done a lot in Europe. As I said already before, one always has to keep an eye on the nutrients. So if you have some manure contains many nutrients, especially phosphorus, which can be used as fertilizer. So whenever you use it energetically, and digestion would be a good idea, but then one has to take care of the nutrients to feed them back to the nature. So that was one question, and the other question that was about this hydrogen storage, and the question was, shouldn't we then store the hydrogen rather, instead of first going into a biofuel and then maybe later either get back hydrogen or or produce electricity from that? And that has mainly to do with the infrastructure. At the moment, there is hardly any hydrogen infrastructure, so nothing like a cavern or so, and especially there's no grid for hydrogen only, which you could reach, which you could use to reach that cavern. While, for example, for natural gas, there's a big pipeline grid, and by the pipeline grid, especially the transport tubes now are bidirectional, so you could actually reach some storage capacity which exists in several countries. So methane can really be stored as a molecule because the infrastructure is there. And in principle, the same would be possible with hydrogen, but it's not there in place. So that is why at the moment it still might make sense a lot to do that. The other reason is also if you start with biomass, then very often, actually, whether you digestion or whether you do gasification, is always methane coming out, because methane is actually what is thermodynamically favored. So the nature actually pushes into methane, and if you wanted to convert that methane, this biogenic methane, to hydrogen, even at relatively small sources, then most probably that would be rather inefficient. So it might even make more sense to first collect the methane, and if you still want to produce hydrogen from that, then do it somewhere more in a unit where then the economy of scale is better, and maybe also the heat integration with the environment could be better.
Thank you, Tilman. And
yeah, maybe I can answer two questions I found in the question and answers. One is from Susan Coelho about countries like Brazil who have biopower from sugarcane, which can complement hydro during the dry season. She asked, is it a flexible bioenergy option? And I have to mention, yes, of course it is. And I'm very unhappy that Brazil was not in our country survey, because this is really an interesting point. Second question I would like to answer very short is to Hans Langenfeld. He asked if could temporary negative electricity prices can also provide incentives to flexible bioenergy production. What is possible is to have bioenergy as a service energy, where you get some money for this flexible for these negative phases. And yes, it can. And for Germany, the amount we talk about additional, let's say, demand in a cent, around a cent. But if you're interested, we have some more studies here. And then the question is corn ethanol, when produced from an overproduction of corn, already also a flexible system? Yeah, I think this is a larger question, these, let's say, balance between food and energy. And this is at least not so much in the focus of our work in Task 44.
Thank you, Daniela. I think with this, we have to conclude the webinar. It's 5:30. I would like to thank all the speakers for their presentations, the audience for providing input. I hope you obtained a clearer picture of let's say, the possible role of flexible bioenergy in technical terms, but also in terms of barriers that may exist, requirements, and also the situation that we're still at the beginning, and that there is still a lot to discover. For us, we will certainly take all your input with us. We are shaping the plans for the coming years, and this is very, very valuable input for that. And as mentioned, please, in the Q&A, there is the link to the website where the presentations will be shown tomorrow. And please also have a regular look at our Task 44 website, for which you saw the link in the presentation of Elina. Well, with that, I would like to thank you once again, and wish you a good remaining day or evening, and stay safe. Thank you very much.
Thank you.